Hi, my name is Aaron Kaufman. I'm a junior in mechanical engineering at the University of Michigan. Through the summer undergraduate research and engineering program, I worked in the energy storage and material simulation lab with Dr. Don Siegel and PhD candidate Max Radin on computer modeling of novel materials for energy applications. My project specifically focused on liquid electrolytes for magnesium batteries. Why study magnesium batteries? Lithium-ion batteries seem to be working great, no? While lithium-ion batteries have proved useful in a number of applications, we will need a higher capacity, lower cost battery for future technologies such as electric vehicles and grid storage. Magnesium has many properties that make it a great candidate for a higher capacity, lower cost battery. First off, magnesium has a bivalent cation, which means its ion has a +2 charge, compared to lithium, which has a +1 charge, so magnesium will have a greater capacity than lithium. Magnesium is also benign, and the fifth most abundant metal in the Earth's crust. All this information about magnesium raises a few questions that I seek to answer. How do magnesium ions interact with the solvent? How do these ions interact with other ions? How do these ions diffuse through a solvent? For my project, I set out to answer these questions by modeling a potential electrolyte for magnesium batteries. The electrolyte is a critical component of every battery, and in this case provides a medium for magnesium ions to move from the anode to the cathode. The electrolyte itself is made up of a solvent and a salt. The solvent I am using is called dimethoxyethane, or DME, and the salt I am using is magnesium borohydride. I use quantum chemical energy calculations and fitting software to come up with parameters for a force field that I use in classical molecular dynamics, or MD simulations. An MD simulation is a computer simulation of the movement of particles. Computer clusters calculate particle movement by integrating Newton's laws. MD calculations are computationally intensive because there are a lot of interactions. For my calculations, if I wanted to simulate, say, 2,000 atoms for 1 nanosecond, the calculations could take a few hours to complete. Once I had developed a measurably accurate model of DME, I could then add the salt. After quantum chemical calculations and parameter fitting to get a force field that accurately describes the interactions of the salt and the solvent, I run an MD simulation of the electrolyte. In this simulation, there are 125 DME molecules and a single magnesium cation. By watching these interactions, we get an idea of the coordination of the particles in the electrolyte. We see that the magnesium is coordinated inside of 6 oxygen atoms. Throughout the simulation, the computer is calculating the radial distribution function, or RDF, of specified atoms. The RDF is essentially a histogram that tells us how densely surrounded the atom is by other atoms and where the other atoms are located relative to the specified central atom. As you can see from the plot of the RDF of oxygen atoms in red around magnesium ions, the magnesium ion is strongly coordinated by oxygen atoms at about 2 angstroms. These plots further confirm the structure we see in the movie of the simulation. From the position data output, I can map the spatial movement of the magnesium ion throughout the simulation. Here is a plot of the spatial coordinates of the magnesium ion. The ion starts at the green point, follows the blue path for 1 nanosecond, and ends up at the red point. This data can be used to calculate the diffusion coefficient, a measure of how quickly a particle moves through a solution. The value of the diffusion coefficient, when compared with values of diffusion coefficients of lithium, will indicate whether the electrolyte is suitable.
This research is just the beginning of even bigger innovations. The next step in the process would be to look at different ion clusters in the electrolyte and to look at electrolyte and electrode interfaces. This research can also lead to the development of new electrolytes that will make magnesium usable. We need to have a deep understanding of our current electrolytes, such as DME, in order to develop new, more efficient electrolytes. We hope that this research will have a significant impact on batteries of the future.